I need to kind of give you a little bit of orientation, a little bit of motivation as to where most of this stuff comes from and why it fits together the way it does. And so before we jump into doing Spark coding, we want to get some of that higher level perspective. So here's a kind of a brief history of big data and how we've arrived at the technologies that we've arrived at today. And what does even the term big data mean? Because it's been used and abused and co-opted by so many different people these days, it's hard to tell. I actually very much like the Wikipedia definition because I think it sums it up rather concisely, which is a big data is a broad term for data sets so large or complex that traditional data processing applications are inadequate. That says it pretty well. It's basically saying once we've crossed over to where we can't do the stuff, we can't manipulate things on our laptops with pandas anymore, now we're in the world of big data. And today, data sets have grown, and particularly in scientific areas and in enterprise areas, commercial areas, data sets have grown so large that they easily swamp those kind of laptop type approaches to dealing with them. So that's where we're in the world of big data, when the data sets are too big to manipulate with simple techniques. Now, at one point in time, that wasn't an issue. We didn't used to collect all the data we could on everything, and we didn't have the space to store it. And so if you have a small amounts of data, you can use inefficient and simple techniques. I mean, for example, grandma's recipe box is a good way to view default organization of small data. Grandma might have a recipe box, and she's organized it by appetizers and entrees and desserts, and that's fine. And if she wants to find a tasty appetizer, she just digs through the appetizer section. Well, what if grandma has a bunch of oranges that are going to go bad and she wants to use those up? So she wants all the recipes that use oranges. Some of them might be desserts and some of them might be entrees. Well, now to find all the orange ones, it's difficult. There's no obvious way to do it. But if we're nice, we can help out grandma. We can take the recipe box, just dump all the cards on the table, and the whole family can go through and look for ones with oranges. And we're going to find out that this approach right here of having multiple workers mine the data is a huge, looming, overwhelming theme of big data. Doing things in parallel allows us to do things that we couldn't possibly do well serially or on non-parallel types of environments. So we'll come back to this time and time again. Now, you might think, well, grandma should have organized her data in some more sophisticated way, but it's difficult or impossible, as we'll see, to organize data in kind of ways that can meet all of the potential searches that you might want to have, or the ways that you want to expand your data, add to your data sets, add to the richness of your data. So sometimes less sophisticated, as a matter of fact, is even better. If you walk into my office, you'll find that in pre-COVID times, you'll find that a lot of my data is organized somewhat chronologically. Things tend to pile up on my bookshelves, articles. And so if I want to find articles from 2007, I can just go dig through the bottoms of the piles, and eventually I get down to that strata that corresponds to 2007. So that's one way you can keep things organized. But if I want to find papers on fault tolerance, for example, I'm out of luck. I'd have to dig through all the papers. Now, if it's an emergency, I've got a publication deadline to meet, and I'm in trouble, then I could go and grab all my colleagues in the corridor, and I could have them dig through the piles and try to find that missing critical paper that I can't seem to find. So again, the notion of having parallel workers come in and help you overcome your data organization or scoping difficulties can be important, can be the only way to solve the problem. But again, you might think that's just because you were lazy and didn't organize your data well. Well, libraries have gotten pretty good at organizing data over the centuries, millennia that they've existed. And so if you go in traditional library and you want to find books on modern physics, the Dewey Decimal System will tell you what section to go to. And if you want to find all the books by Wheeler, the card catalog will help you to find that. And you might think, yeah, see, good organization can help you to overcome the fact that you've got huge amounts of data. But what about something as simple as, what if I want to find all the books by Wheeler where he's not the first author? Now I'm in trouble. Even card catalogs can't solve that problem. So it's not hard to come up with searches that defeat whatever organizational scheme you're going to come up with. Once again, your only hope would be, I got to recruit a bunch of librarians and we could go up and down the shelves and or dig through the card catalog and find all the books in that section where Wheeler isn't the first author. That's the only prayer we have. The reason for this today being such an issue is that data has really grown enormously. At one point in time, data was expensive to store, and so we didn't just store everything we get our hands on. This is what 5 megabytes of data used to look like back in 1956. And it cost an awful lot of money too, hundreds of thousands of dollars then in those bucks. Now, that's causes you to not casually just store, again, all the data you've got, all your old data. Instead, the issue is very much, what can we throw away? It's not so true anymore. Today, for $130, I could buy myself an 8 terabyte drive and store everything I've got sitting around. I really don't have to think about throwing out old photos or stuff that old digitized documents. Why not keep it all? And as a matter of fact, that's the new theme in again, not only science but in the enterprise world, is with storage so cheap, why not keep everything? Data today is seen as a really hot commodity in the enterprise world, so everybody just keeps everything. So whether it's Facebook or in the world of deep learning, you want to have big data sets, as we'll see. So you want to keep enlarge your training and data sets as much as possible. The Internet of Things is out there with lots of devices like your Fitbits and whatnot generating data. And in science, we have many of our own cases that are good examples of this. We've got things like in the astronomy world, we've got sky surveys, where we're doing every single night. These instruments are generating more and more high resolution data that they want to keep all of, or radio telescopes, day and night, they're gathering data. We've got genome sequencers out there. There was a point not that long ago where sequencing the human genome for one human was a big accomplishment. Now we're sequencing genomes for everybody all the time, constantly. And accruing this data is a valuable thing. And so we're keeping all of this data, even in things that you're less likely to think about, like the digital humanities. Have dived into big data, where they're now digitizing every archive they can get their hands on, so that a researcher no longer has to travel the world, going into dusty archives and museums to compare and contrast different types of things. You got lots of scientific instruments out there, those satellites and buoys sitting in the ocean environment for climate monitoring. The list is endless, and I could go on for a long time about just projects I've individually been involved with. But the point being that today, keeping data is the thing we do. And so today, so many data sets are big. People used to define big by some silly thing like how many bytes is your data, basically, and it used to say if it's more than 10 terabytes of data, that's getting biggish, because that's about the size of a Library of Congress. If you hung around big data, or you do hang around big data, you will eventually, somebody will make a comparison to a Library of Congress amount of data, which is silly, because the original estimate was ridiculous, and it continues to be kind of simple-minded to think of big data sets as just how many bytes are they. Instead, big data can be big and unmanageable for a variety of reasons beyond size. So you do have size. Lots of data sets we can just say, hey, they're huge, and that makes them difficult to manage. Genomic databases tend to be pretty big. Common crawl, web-based database sets, things that for people that are interested in the semantic web or benefiting from the trove of information that is the web and its diverse dimensions of data. Those data sets tend to be pretty big. And so I could go through endless examples of this kind of stuff. And we try to host a lot of those big data sets on Bridges, just enable researchers to not have to go out and move them around or host them themselves. But that's not the only way to think of data as big and difficult to work with. You've also got throughput. In other words, how fast are you accruing data that you've got to cope with it, both in terms of storing it eventually, but also in terms of processing it so you can store it and can throw out the data you don't need. And if you think that, well, you can overcome that with enough money to just buy enough disk, well, think again. For example, a square kilometer array, which is a radio telescope project, it's being built in phases right now, will eventually, by the end of the decade, scale out to where we'll be generating an exabyte of raw data per day. They hope to, with a tremendous amount of data processing, using the techniques we're going to talk about in this workshop, compress that down to 10 petabytes of data per day that they'd like to keep permanently. So, you're not going to overpower this just by having enough money to buy disks. Also today, there are plenty of scientific instruments as well as consumer devices that are constantly streaming data. Things like, the Fitbit that you might wear on your wrist is an obvious one, but there are plenty more out there. Civil engineering world is embedding devices in bridges and buildings and whatnot for maintenance purposes and monitoring purposes. Scientific world is deploying drones and buoys and all kinds of devices out in the environments. People are just, assuming these days that streaming of data is a routine and regular and supportable thing to do. And we'll see techniques for dealing with this. Spark is good with this kind of stuff. A third way that data can be difficult to deal with is that it can be very complex in its structure, so that it becomes difficult to, day by day, to say exactly what it's going to look like. Today, it's very desirable to be agile to where you can add new things that you weren't previously capturing or never even thought about capturing into your database. We'll look at some more examples of this. One I'll point out right now is, for example, the GDELT database, Global Database Events, Language, and Tone. It's kind of a news database that tries to capture newsworthy events in a single database for analysis later. It's only a couple terabytes per year, which is pretty efficient, but it has a lot and a growing number of fields trying to capture every type of news event. When you first come up with a database to capture news events, you might think, I need to capture the time and the location, maybe the country. But then as you do it more and more, you begin to realize that there are lots of things that you forgot that you needed to capture, maybe people involved, or maybe political parties, or maybe medical things, all kinds of fields that eventually become useful to capture that you didn't, again, on day one anticipate, or maybe even in year 5, you still want to add new things. And that ability to make your data, your table-based data, right, which you used to just have your rows of data, newsworthy events, and then the fields to capture that data, to be able to add fields at will to a database in mid-flight, as it were, is today a very important capability. And you end up with a rather complex database. At any rate, this is another way that data sets can become difficult to manage with traditional techniques. We're going to look at how to deal with these kind of data sets as well. I think of this as the 3 V's of big data. You've got volume for their size, you've got velocity for the throughput, and you've got variety for the complexity that they can have. These together can characterize, when something is big and difficult and exceeds your capability with old school data, analysis techniques. And by old school, I mean, pandas on your laptop. Okay, let me see if there are any pending questions. Let's see, data points. Is there any point how many data points you have makes it big data? Nope, not really. It's a combination of factors like we were just talking about here. Let's see, the other ones the TAs have picked off. Somebody else has added 2 more V's, value and veracity. I guess those are not unfair things to consider as well. And we'll talk about maybe not value so much, but veracity to some extent when we start talking about the reasons we organize the data we do. We'll be very shortly getting to that. And let's see. Okay, and the rest of the questions the TAs are dealing with, they're just logistical issues. Okay. Well, at one point in time, the default for organizing data was just table-based data, in a relational database, and use, fairly standard SQL type API to get at your data and organize your data. And a lot of the famous databases, Oracle, database, MySQL, SQLite, these are all kind of built around that paradigm. And this became, again, over the decades, became the fairly standard way to organize data. Now, why did this become unfashionable for a period in time? I say it wasn't fashionable. It's become quite fashionable again to like data in tables. But at any rate, for a long period of time, the NoSQL movement, that was literally the name of the approach to dealing with data, was NoSQL. We're not going to do SQL. We don't, we have other alternatives, just not SQL. The NoSQL movement became quite popular because this is unattractive for a number of perspectives that big data brings about. Number one of which is that it's not agile. It's not easy to rearrange and reorganize all of our data on a whim. The schemas, the organizational schemes, are kind of set in stone. That's not entirely true. You can go back and refactor a table-oriented database, but it's not trivial or friendly or efficient to do. Instead, you hope that on day one, when you're setting up your tables, you mostly know what you want to do. So if you're setting up a company, you got payroll and inventory and your contact information. You don't anticipate that in year 2, you're going to be rearranging all of that information. You kind of think you know how to run a business, and that's fine. As opposed to us deploying a scientific instrument in the ocean, which was capturing just salinity and temperature. But now we have this new capability in version 2 of the device. They can capture GPS coordinates. And then version 3 came out. So some of them now can capture, can move up and down and capture barometric data or whatever. So, with modern approach to it, we want the ability to just on a dime be able to throw in new diverse types of data. Maybe very different types of data. Maybe we want to capture, for example, everybody's heartbeat. We were originally designing some fitness database. And now we want to capture something that's corresponds to, heartbeat by the second, right? So now we've got some huge time series data set that we just want to throw into the database. That's modern database approach. We hope we can do that kind of stuff. SQL, also, if the data is organized in a way that's difficult for certain types of searches, where we're joining certain types of tables in painful ways, a search can take an awful long time for a large SQL database. So anybody that has experience in database administration knows that eventually one of your users is going to come up with a search that, instead of taking the 1 or 2 seconds that it normally takes to access the database, for some reason takes 3 hours. And they will come to you complaining, why does SQL search take 3 hours? And it's because it's doing a join between tables. It's got to go back and forth and combine tables in a way that's jumping all over the entire data set. And those kind of cases are painful to deal with. So wouldn't it be nice if we could have a database that just doesn't run into those problems? We're going to find out that's not entirely possible, but we might have that hope. Another thing is that data sets grow very large, and we start talking about terabyte and petabyte data sets. It's not quite as easy to back them up or to distribute them around, which is useful for multiple reasons. The backup reason's obvious for resilience and fault tolerance. Distributing them around is useful because it makes it easy to access from multiple cores, multiple helpers that are helping us to search and process our data. That's not as easy to do with an SQL database. You can do it, but it's not trivial. We'll see some other databases where it's very easy. But the main reason that SQL data organization schemes or relational, table-oriented databases became less fashionable is that they are costly because they give us some very nice guarantees about how they'll behave. Over the decades, they developed these guarantees, which eventually became codified for most people into ACID guarantees, basically very well formalized protocols that said, this is how our data sets will behave, that said, this is how they'll work in terms of fault tolerance and errors, people trying to enter bad data, people accessing the database simultaneously. We've got hundreds of people writing the database at once. How do you keep a given record from becoming corrupted? All of these kind of protocols were combined in ways that gave a really good guarantees, but were very costly. Now, your bank is very much interested in this. Your bank is very concerned that the database not be in some weird state at any point in time, ever. So your bank has your bank account sitting there. And even though your bank account might be accessed by you when you're on an ATM in some other country on vacation, it might be accessed by a utility company that's doing an automatic withdrawal from your account. It might be accessed by a credit card company, and it might be accessed by the bank itself, adding interest into your account, all at the same time. And yet, even though they're all accessing your record at the same time and updating your balance, it's very important that not a penny be lost, right? It would be very uncomfortable for you if your bank couldn't explain to you exactly how your balance got to its current state. ACID databases are fantastic at that. They say, regardless of how many people are writing to a record at the same time, that's fine. Regardless of the fact that the power may have gone out in the middle of one of those accesses and you had a problem, we can roll back and reconstruct things. Those guarantees are great, but they're very expensive in terms of how much overhead they add to any given transaction. In particular, the number one thing they do is they make it hard to do caching. And caching, or keeping local little copies of the data around, is a very, very useful thing in terms of speeding up performance. But it's hard to do that. We can't have everybody have their own little copy of your bank balance and be mucking around with that and doing calculations on it, and then later on trying to figure out how to combine them together. That's a complicated and error-prone process. So instead, SQL databases kind of coordinate all of these transactions, but it's expensive. Now, let's take a look at something that does the opposite of that, like Google searches. If I do a Google search on something and I want to find out what the 5 most popular kittens on the internet are, and I do a search right now, and I come back with the first page of results. And if I do a search 5 minutes from now and I get slightly different results, I don't freak out, right? I don't get on the phone to Google and say, what's going on? Your results aren't the same from day to day or even minute to minute. Instead, we acknowledge that for a lot of big data mining, we take these kind of, close enough results. So for Google, maintaining ACID type consistency in their database and determinicity in search results would be silly, very expensive. Instead, they have their databases scattered all over the world in different data centers, copies of it. So when you do a search and somebody else does a search, they can be going to very different out of sync sets of data. And when I do the search twice in a row, it might even be going to different data centers or collecting the data in different ways. And you know what? That's fine. That's fine for a Google search. And so they don't want these kind of guarantees. So this is the reason why SQL type data became unfashionable. And so keep this in mind as we look at approaches that we are going to use, which will forgo this and not give us all these guarantees, but as a trade-off, they'll be much, much faster. Okay, so one way we can just ditch all of this organization right off the bat is we can go to the simplest possible way of organizing data, which is a key value store. And we'll find these are everywhere these days, and we're going to leverage them ourselves to our great advantage. And there are lots of them out there all over the place and even built into APIs and things that you're using. And a key value store says, okay, forget tables and preset structure. Instead, our database is going to be as simple as I'm going to give the database a key and it's going to return me a pile of bytes. It's going to give me a value back. So I give it a key, and that key can be anything. It could be an integer, which is probably what most of you are thinking who are classic database administrators. You're giving it an index to the database. But it can also be a string that's got a lot of structure to it. It could be any kind of text string you can imagine. So I give the database this string, and it gives me back a pile of bytes. And that pile of bytes might be some numeric data, or it might be a picture, might be a WAV file. It's not worrying about it, just giving me a pile of bytes back. It's up to me as the user to be aware of what those bytes really are, how they're organized. Now, this is very simple-minded, but it's also very agile. We don't have to worry about accommodating new data types as we decide we want to include our heart logging information from our Fitbits into our data set. We just start throwing them into the database. And it might be a totally different, it's time series data of floating point values or something. And that's very different from the picture that we also have in the database and some text and user addresses, but we just lump it all in there together, as long as we can get to it with the right keys. It's very scalable. If we run out of space, we just buy some more drives and keep writing data to those drives. As long as we've got a good hash, in other words, as long as we've got a good algorithm that say, given the key, can it go and find kind of the right drive where that data might be sitting, we're going to be in good shape. And hashes are a very well developed area of computer science, so it's not hard to come up with a hashing scheme that's workable. We can back this stuff very easily, just start copying drives, and stuff can distribute around and very easily. So this simple-minded scheme buys us a whole lot in terms of this kind of flexibility. And by the way, again, before those of you who, when you think key value, think, I'm giving it an integer or some kind of index and it's finding me the data. This is a very common kind of key structure right here. And so for an online shopping cart, for example, which key value stores are used a lot for session information, the key might actually be this string right here. Might be something that says cart and then a username and then maybe a timestamp here. So the key itself can have a lot of structure, including something like a timestamp. And that can go back and get me the shopping cart with all that information. So key value stores are wonderfully flexible. Let's see. Looks like, let me go back and answer the more technical questions here. It's possible to run ML techniques on SQL databases without exporting it? Absolutely, and we're going to look at how we can do that. Spark will interface directly with SQL databases and machine learning techniques. So yes, it is possible. We don't have to worry about how to get data from a table-oriented thing into some more modern format. SQL is a modern format. As we'll see, SQL has come very much back into favor in various forms. Let's see. Okay, Cassandra uses a slightly different approach. Well, we haven't gotten on all the approaches yet, but there are very different approaches with different, and we'll get some different ones here with different emphasis on how they organize data. Okay, how does giving up all of these guarantees and just having a bunch of disorganized data and everything, again, it's flexible certainly, but how does that solve our problems in terms of finding and retrieving stuff? Well, remember before I said, if we have an army of librarians just searching through the shelves, they can help us to find things. Well, that continues to be the case here. If we have today an army of compute cores in our data center, they can help us charge through this relatively unorganized data. So this is the key to making this key value and other simplified approaches work, is we've got massively parallel computing behind the scenes doing all of these searches and sorts and other types of analyses, more complex analyses we'll see, machine learning types of analyses on our data. So this is the difference in what allows us to be disorganized, is that we've got parallel computing frameworks behind the scene. We're going to very much take advantage of that in our workshop, but in a friendly way. Fear not, again, those of you that think, oh, we have to learn something about parallel computing. Not really. It's the people that wrote these software tools that had to worry about that. Okay, now as people got very enthusiastic about these simple key value store kind of approaches, they also realized that at some point it is kind of nice to have some organization of your data. data, usually inherently has some organization to it. And if we want to start doing more complex searches through our data, it's nice to be able to do things like say, hey, can you get me all of the records that have a plant type of daisy? If I've got a botanical database, for example, I want to find all the daisies in that database. And so that means then to even say something like this, plant equals daisy, you're making some assumptions about the data being organized, that it's even text data, that it's got fields to it, like something, a plant field in it. So it is nice to be able to assume that our data does have some fields in it. And so that moves us into document store type databases. And this is where we do have Cassandra and Couch, MongoDB, and databases that say, okay, we do at least guarantee we can do some basic searches and analyses on the data, but we want to still be very, very flexible. So all we're going to say is that our data is in some kind of format like XML or JSON or binary JSON, is probably most common these days. So it's an object that can be very, very flexible, but at least it's got something where we can start to issue some queries on the data objects that we might retrieve back. And different databases have very different approaches to this. Some of them are saying, well, you're mostly going to be writing data. Some of them are going to say you're mostly reading data, or you're doing a mixture or whatever. So they can take different approaches to the way they behind the scenes organize and optimize things, and that gives them different performance capabilities. But the general theme of a document database is that the actual object that's returning has some structure, but a very flexible structure. Just saying something's JSON isn't telling you a whole lot about what's in there. It can contain almost anything. It can contain pictures and WAV files and all kinds of textual database and hierarchical organizations. But it at least gives us the ability to do some kind of processing on the object that's returned. So that's why this has become quite common and popular way of actually organizing data. On the other hand, you may say, I actually like the notion of having bona fide fields that I can access my data with. But I don't want to be trapped into those fields. So this is, for example, the Google GDELT database, the news database I was talking about earlier. You do want to have fields attached to every news event, or in this case, we have users. We want to have some information attached to every user, but we don't want to commit 100% in advance. And as a matter of fact, each user might have different data that we know about them. So here is a wide column store. And again, the common ones, Cassandra, Google Bigtable, Apache HBase, these are some wide column stores. We have, for each user, different information. So Joe, we have an email address and a web address for. Fred, we have a phone number, an email and address. Julia, we only have an email. Mac, we've got a phone number. So we have different things. And somewhere down the road, we might decide that we even have some new identifying. We might want to have a social security number or something that we hadn't thought about initially. A wide column store allows us to kind of very easily add new fields in. Because what it really is, or the way I think of it, and it's a perfectly valid way to think of it, I think it was a 2D key value store. First, we give it the key for the user, and then we give it another key for the field that we want to retrieve. And that gives us an awful lot of flexibility. So we can be very agile and non-committal up front, but we can still treat this kind of like we've got fields for each one of our records. So this is what a wide column store looks like. The last thing I'll talk about here in terms of major paradigms for organizing data is one that's very often overlooked, but incredibly important. I think it scares people at first, and then once they get comfortable with it, they realize they shouldn't be scared or intimidated, which is graphical databases. Graphically oriented data is fantastic for anything that's kind of semantic, web-oriented data. If you're going over the web trying to find data and analyze data, the web's very obviously a graphical type organization. On the other hand, it's also great for graphs. And I say this only half jokingly here because people tend to be let me go back a second. People tend to be very intimidated by the notion of graph database. And yet anybody that's taken a basic programming course, you dive very quickly into those courses into graphically organized data without even thinking about it. Anything that's a linked list, for example, or most of your lists in say Python, anything that's a linked list is graphically organized. You've got that one thing connected to another. And very quickly, when you dive into applications, you find yourself with data sets and models that are graphs. And you're happy with that. The notion that something is a graph makes a lot of sense. It's only when you start to think about these particular issues that people tend to get a little bit scared. Like, how do I actually serialize? How do I write this stuff out? I've got it as a graph in memory in my computer algorithm, but now I need to save it as a data set to disk. There's permanent storage. That takes some thought. Later on, I want to retrieve it from disk, or I want to retrieve a portion of it from disk. So now you start to think of it as a database that's graphical. That's where people get a little bit uncomfortable. Or you want to visualize it. Everybody can visualize the toy problem, right? That looks like this, but the real database ends up looking like this when you start populating with real data. How do I deal with things that visualize like this and finding relationships? And how do I even query things? For example, queries in a graph database can be very different, fundamentally different than from table-oriented data or a key value store. For example, in a graphical database, I can ask a question like, how many of my friends have 6 friends? Right? I can ask a graphical relationship about how things are connected to each other. You can't possibly ask that kind of question in an SQL query. You can fabricate some iterative things and everything to make that kind of work, but it's going to be expensive and awkward, unnatural. You can very naturally ask those kind of questions from a graph database. So for those of you that are familiar with the 6 Degrees of Kevin Bacon game, right? How do I relate every movie back to Kevin Bacon with 6 links of actors and actresses, right? You can go to the internet database and get all the data you need. And with a graphical query, you can ask questions like that. So anyway, these type of problems arise very naturally and they're very common in the real world. People seem to be comfortable with them as algorithms. It's only when you start talking about actually dealing with them as a data set and a database that people think it's exotic and difficult. And they shouldn't, because it's not true. The technology to deal with this is pretty mature these days. The first and most common one for a long time was Sparkle, which is actually a World Wide Web Consortium standard, which treated all these databases as triples. So everything was, subject, object, verb, or you could, everything had, was how it related to one other link in the graph. And that works, actually. You can make that work, but it's a little bit limiting. So for a while, the proprietary Cipher approach was out there instead, which is a little bit more flexible and allowed you to work with subgraphs, deal with weights in graphs. So these connections might actually have weights to them to represent things that can be important. The original 1.0 standard didn't deal with that. So anyway, the standards have evolved. These days, Cipher is no longer proprietary, so it's become quite popular as it's become more open. And you can deal with more flexible cases. But anyway, you have options to use. So if you need to deal with graphical data, you're not starting from scratch. You have databases and query languages which are built to accommodate that stuff out there. And you certainly shouldn't think of them as niche approaches, because they're huge parts of what drive the web infrastructure today. Microsoft Bing's Knowledge Graph, for example, Facebook, Google's Knowledge Graph. I mean, these are all graph databases behind the scenes for how they operate on stuff, and they're very large and growing all the time. And they allow you to, again, deal naturally with the way the data is organized. So don't be afraid of graphically organized data. Okay, but it brings us to the big question here of Hadoop and Spark. What kind of databases are these? Because it's a big part of our agenda here, especially this morning, is Spark and Hadoop. And we're going to apply Spark over the next day and a half to a lot of different problems here and machine learning and everything else. So what kind of databases are they? And the answer is they are not databases. And the short answer that people will throw at you is that they're frameworks for doing big data analysis. And then they walk away like that's a meaningful statement. Oh, it's a framework. It's not a database, it's a framework. Well, what does that mean? It's kind of meaningless without a lot of context. We're going to give you that context. We're going to be using these tools here. The idea is that we saw that doing things in parallel, having us sit around and help grandma in parallel, or having our data center work on a simple-minded key value store in parallel, gives us the ability to do things we couldn't possibly otherwise do. Well, you don't want to become a parallel programmer just to enter the world of big data. So the parallel programmers out there instead have built these nice frameworks for you to do it. I say nice. Well, Hadoop wasn't so nice. As we'll get into in a moment, it was kind of very low level and primitive and difficult to use. Spark is much, much nicer and higher level. That's why we're going to focus and leverage it. But historically, it's important to understand Hadoop. As a matter of fact, this is the first workshop where we haven't broken out Hadoop as a separate topic. The earlier iterations of this workshop years ago, Hadoop was a big separate lecture, and we dive deeply into the details. And over the years, Hadoop has become less and less relevant. And today, nobody would indeed start a Hadoop project from scratch. You might inherit some Hadoop, but you're not going to start a Hadoop project. And so this is the first iteration of this workshop where we're not breaking out Hadoop as a separate talk. We're just going to quickly cover it before we jump into the real star of the show here, which is Spark. One of the sparks for us doing this here was that as we moved to Bridges 2, we weren't even initially planning on putting Hadoop on Bridges 2. That's how kind of moot it's become. That's not to say it's not important. So we're going to talk about it a little bit here, because Hadoop was, first of all, the predecessor to any other approach, in particular Spark. So I draw it here as kind of Stonehenge. So you got to take a first shot at things, and Hadoop was the first. It answered a lot of important use cases back when there was no other alternative. So it's easy to make fun of it now, but it was the only thing we had for a long time. Today, Spark is going to make things a lot easier for us. So, but I don't want to be too arrogant. I draw Spark as the pyramids here. It's not a skyscraper. We're not quite done yet. Things are still rapidly evolving, but Spark is certainly a huge advance over Hadoop. So, and we'll find out that SQL has made its way back into this stuff as well. It's no longer the case that SQL is beneath us, but we'll come back to that. So what is Hadoop exactly? Well, Hadoop is a programming platform, so it gives us the ability to program some of this stuff. It's also a distributed file system to enable that stuff. It's also a parallel execution environment as part of the framework, and it's also a software ecosystem with lots of pieces that come together to make all these things happen. So it's kind of a lot of pieces here to enable all this parallel computing. And the fact that it's all these separate pieces is one of the reasons it wasn't quite so friendly to use. It also had as its programming environment pretty much a single-minded mindset as to how to do all of your data analysis. It's called MapReduce. So it kind of introduced the concept of MapReduce to the world, but it also insisted that we think of everything in terms of MapReduce, and that's not particularly friendly. So the idea of MapReduce is that we have a bunch of data, and we can take and we can transform each element of that data. Excuse me one moment. Pardon me. I'm staring right into some lights, so for some illumination here, and it triggers my sneeze reflex. As I was saying, MapReduce basically says we want to take all of our data and we want to transform it with these mapping operations, and then we want to reduce it down to some subset of that data with these reduce operations. Well, that might not seem like the most natural way to approach every problem, but it's the way we got with Hadoop. And the more you work with this, the more experience you get, the more you realize it is actually very flexible, and you can do an awful lot with this. Pretty much nothing you can't do with this, but it's just not the most natural way to approach every problem. But it's the way with Hadoop that we were kind of forced to approach every problem. So we take our data set, we can work on the elements of data and transform them into something else, and then we can boil them down a little bit more, and then we can do this iteratively until we finally come up with the answer to our data. And again, that might not seem like if your data you're starting with is all of your customer data, and the answer you want is who should we send promotional coupons to, being forced into this framework might not seem like the most obvious thing, but it's what we had. So Hadoop also had attached to it a file system, which is a parallel distributed file system, which is necessary since we want to do all the stuff in parallel. By the way, that's the motivation for this. These operations lend themselves to mapping onto parallel machinery very well. So if you do maps and you do reduces, that uses the parallel machinery in a way that's easy for the programmers to map to, the people that are actually implementing stuff behind the scenes. Not easy for the users, but easier for the programmers. Okay, well, the parallel file system also works nicely in parallel with all the parallel resources you have, and it can do replication, and it can allow us to distribute the data when just in advance of us doing any analysis on the data. In Hadoop, it's very much a write once, read many approach to the data, is that you want to write your data set out there and you're only going to read it. So if you need to change your data, well, you got to make a whole new copy of it to write to disk. So the idea is we're mostly reading our data there. You're not going to go back and randomly access any given element of the data. That's kind of an approach, a limitation, an optimization is another way to think of it, of the Hadoop file system. And it's built on top of some underlying file system. So your normal generic file system that you have on your Unix system is used to build this HDFS file system on top of it. Let's see. Let me defer the Spark questions a little bit because we're going to get into the Spark. So I'm going to stay with, we'll answer your Spark questions. We're going to get into Spark very shortly. So I'm going to hold off on all the Spark questions. They're good questions though. Okay. And we're going to tie up Hadoop pretty quickly here because, like I said, Hadoop has become obsolete, but it's important to understand, to brief to understand what it offered and what the pieces of it that remain around still offer. It had behind the scenes this scheduler that attached to it to allow us to to execute all the stuff in parallel, right? We got this parallel file system, and I said we got these programs we wrote to do stuff in parallel. Well, that means at some point the user wants to, wants to actually run the stuff. Well, the scheduler to grab all the resources in parallel and run things distributed and coordinate them with where the data happens to be sitting and everything else was called Yarn, yet another resource negotiator. And it would do all the stuff in parallel behind the scenes for us as much as possible. So to use Hadoop, you'd load the data into the file system, then you'd write a program. Java would be the most native way to do it, since that was kind of Hadoop's native operating framework and API. But you could also use the streaming interface, which basically said I could write a bunch of scripts in pretty much any language, as long as they did a map operation and a reduce operation. Hadoop would take and just run those processes in parallel on our data set. And so you could even use built-in Unix utilities to do, operations to reduce data and transform data. And you could write in other languages as well. Like we could write Python scripts here to do this Hadoop streaming stuff. And when you get all your pipeline constructed of your streaming from one piece to the next, then you'd submit a job and it would process everything. And so that was the way that Hadoop operated. And if you got the skilled people together to construct that pipeline and do this job, then all somebody that's a user would do is trigger this job. Maybe it would run overnight, maybe it would run in a few minutes, and it would go out and do all this complex stuff. But you can see this is kind of low level and primitive and difficult to use. So you can do it, pretty easily if you know exactly what you want to do and how you want to connect these pieces together. So if you get some proficiency with it, so here's an example. Later on, we're going to do with Spark a very simple example. It's the reason I bring this up. With Spark, we're going to analyze Shakespeare in depth. But if we wanted to do, say, a word count on Shakespeare, we could use the built-in Unix utilities of cat to stream the file and view the file. I don't assume you know these. Don't worry if you don't. We could use the word count utility that's built into most Linux shells as well. And we could go and construct a Hadoop job here that takes and streams these two pieces together and does a word count on a Shakespeare file. And it looks like this, and it connects the right pieces together, and it does this operation. So you can do it, and it's workable, and people did struggle along with Hadoop and do a lot of useful stuff for a long time. But we don't want to. On the other hand, why I'm even mentioning this and why it's important is not just to point out what was important in the past, but a lot of the pieces that were developed to work with Hadoop, the whole ecosystem that grew up around it, became very useful and still live on. So Hadoop may be gone, but it left behind a whole lot of stuff that we still find useful today. The file system is extremely popular. And as a matter of fact, it's maybe the most popular file system that people use with Spark because they want a parallel file system. Well, the two parallel file systems are well understood and how to deploy it. But a lot of other pieces too. Protocols that connect up different data formats that Hadoop would work with. Lots of different databases themselves. All these different pieces, and there are lots of them, that Hadoop generated and created are useful by more advanced modern approaches, in particular Spark. So that's the reason why you'll still see a lot of Hadoop legacy live on and be relevant today. But we don't want to deal with it anymore. And again, today you'd never start a project using Hadoop, but you might inherit it.